Hi everyone. Before I start, I would like to thank the organizers and everyone that made this book. The title of my talk is Characterizing some classes of rings via Superstability. The idea of the talk is to study classes of modules as AECs. As I know that some of you aren't that familiar with AECs, I'll begin by giving some quick background on abstract elementary classes. So abstract elementary classes were introduced by Shella in the late 70s to capture the semantic properties of infinitary models. An abstract elementary class is a pair, k less or equal to k, where k is a class of tau structures and less or equal to k is a partial order on k. Among the axioms, we have the Tarski-Bott axiom, which tells you that you are closed in their union, and the Logenheim's column-Tarski axiom, which is some sort of downward Logenheim's column assertion. Now, compared to first-order model theory, abstract elementary classes have way more freedom. First of all, the class k doesn't have to be first-order axiomatizable. And secondly, for a fixed class k, you can choose the relation you want to study on k. This is impossible in first-order model theory because in first-order model theory, you always look at the models with respect to elementary substructure. I'll make more emphasis on this later. Now, before I go on, let me introduce some examples. So we have the class of modules with embeddings, the class of modules with pure embeddings, the class of absolutely pure modules with pure embeddings. For those of you that aren't familiar with absolute pure modules, these are the modules that embeddings become pure embeddings, and flat modules with pure embeddings. Now, flat modules, for example, in the class of abelian groups, are just torsion-free abelian groups. Now, as the pure submodule relationship will appear a lot, let me remind you what it is. So M is a pure submodule of N if and only if for every A bar in M and phi an existentially quantified system of linear equations. If N satisfies phi of A bar, then M satisfies phi of A bar. So being a pure submodule is stronger than being just a submodule, but it's weaker than being an elementary submodule. Now, the next two properties aren't satisfied by all AECs, but they are satisfied by all the AECs that I'll introduce in this talk. So K has the amalgamation property. If you can any span of models, you can complete it to a commuting square. K has the joint embedding property. If you have any two models, there's a model above it. And K has no maximal models if every model has a proper extension. Now, as AECs are a semantic object, the first order notion of type doesn't make a lot of sense. So shall I introduce a semantic notion of type called Galois type? We will denote by GS of M the collection of all Galois types over M, and we will say that K is lambda stable if and only if GS of M is less or equal to lambda for every M in K of size lambda. Now, the next two notions were introduced for first-order model theory, but they are very important for us. So we say that M is universal over N, if and only if M and N have the same size. N is a K substructure of M, and for every N star in K of size M, such that N is K substructure of N star, there is F from N star to M fixing N. Now, with this, we can introduce limit models. These were introduced by Coleman and Shella as a substitution for saturated models on AECs. So let lambda be an infinite cardinal and alpha less than lambda plus a limit ordinal. M is a lambda alpha limit model over N if and only if there is Mi with I less than alpha containing K lambda, an increasing and continuous chain such that first M0 is N, secondly the union of all the Mi's is M, and finally Mi plus 1 is universal over Mi. The way we're going to work with this is that lambda will be fixed and then the alpha is a parameter that will be moved. Now, you might ask, how do the limit models look like in a particular example? So in abelian groups, we have that G is a lambda alpha limit model if and only if G is isomorphic to precisely this thing here. The way one proves this is first you prove that G is divisible, and then this thing here is just the maximal divisible abelian. Okay. So the first question one might ask regarding limit models is, when do they exist? This was answered by Shella. So let K be an AEC with JP, AP, and non-maximal model. Then K is lambda stable if and only if there's a limit model of cardinality lambda. Now, as a model theorist, the second thing one might ask is, okay, so for a fixed lambda, how many non-isomorphic limit models there are? In this case, we are actually just gonna look at those classes where there's exactly one model for each cardinal lambda. So we say that K has uniqueness of limit models of cardinality lambda. K has a limit model of cardinality lambda, and a given M and N in K lambda limit models, M and N are isomorphic. Now, with this, we introduce the notion of superstability. So K is superstable if and only if K has a uniqueness of limit models in a tail of cardinals, i.e., there is a cardinal lambda such that above that lambda you have uniqueness of limit models. Now this looks very different than first order superstability, but actually they are equivalent. So for T, a complete first order theory, the models of T with elementary substructure is superstable if and only if T is superstable as a first order theory. The way you go around it is you show that limit models are saturated models, and once you know this, you know that any two saturated models are ideal. Okay, so this is all I want to say about AECs in general. So now let me introduce the setting I'll be working for most of the presentation. So let R be a ring and T a first order theory, not necessarily complete, extending the theory of left star modules such that first, T has an infinite model, and secondly, T is closed and direct sums. Now let KT to be the models of T with respect to pure embeddings, and let the size of T to be the size of R plus 11. Now, I want to point out two things. First of all, we're interested in particular in those theories that are incomplete. The reason for this is because first, everything is known about complete theory of modules, and secondly, if you look at an algebraic example, in case it's first order axiomatizable, it's very unlikely it will be axiomatizable by a complete theory. More likely that it will be axiomatizable by an incomplete theory. Secondly, so why do we take K of T to be the models of T with respect to pure embeddings and not say with respect to embeddings or with respect to elementary embeddings? The reason for this is because pure embeddings is a natural algebraic notion, and secondly, from the model theoretic point of view, it is known that a complete theory of modules has PP quantifier elimination, so that's why we choose this particular relation. Even after this explanation, you may say, okay, there are not that many examples. Okay, so let me give you some examples. So modules is an example, torsion of 3 abelian groups, chi where chi is a definable category of modules, absolutely pure modules for R left coherent, flat modules for R right coherent. Again, in these last two examples, we have the extra hypothesis of coherence. The reason for that is because absolutely pure modules are first order axiomatizable if and only if the ring is left coherent. And the same happens for flat modules. But actually, as we will see later on this presentation, we can say a lot about these two classes without the coherence of each. But before we do that, let's go to some basic results. So these basic results are joint work with Coursera. So KT is an AEC with joint embedding, amalgamation, and non-maximal model. And if lambda to the T equals lambda, then KT is lambda Galois stable. Because of the theorem we mentioned of Chalat, we actually have that in this setting, then limit models. If we want to characterize uniqueness of limit models, let's see what we can prove about them without any assumptions. So before I do that, let me recall the following algebraic notion. So M is pure injective if for every n with M pure submodulo of n, we have that M is a direct sum of n, i.e., there's an M prime such that n is a direct sum of M and M prime. Now, what are we able to prove about limit models in general? We're able to prove that if M is a lambda alpha limit model with big cardinality, then M is pure injective. And if M is the lambda omega limit model and N is the lambda T plus limit model, then M is isomorphic with countably many direct copies of N. So this tells us that we know how big limit models look like, and we know how the first limit model looks like. Moreover, in joint work with Tommy Coursera, we were actually able to show the following, which actually is true for basically any class of AECs, any class of modules of AECs. So if M and N are limit models in KT, then M and N are elementarily equivalent. The reason this is true is because we use PP quantifier elimination. Now, because of this result, I came up with the following theory. So for T a theory of modules, let M hat of T be the 2 to the T omega limit model of KT. We know this exists because we have amalgamation, gender bending property, and maximal models. And moreover, we have a stability in 2 to the T. And then we let T hat to be the theory of M hat of T. Now, why is this nice? First of all, we know that every limit model satisfies this theory. Secondly, every model of T hat embeds purely in a model of KT. And thirdly, T hat is a complete theory. And complete theories of modules are very well understood. So what we want to see is how close is T hat from K of T. So I proved some relationship between these two classes. So for lambda greater or equal to T, they have the same stability cardinals and limit models. And for lambda greater or equal to T plus, they actually have the same saturated model. Because of this, we can take information from KT, send it to T hat, then do something T hat, and then send it back to KT. Now, before I go on, let me introduce what sigma pure injective modules are. So M is sigma pure injective if and only if the module obtained by taking countably many direct copies of M is pure injective. Now, why are these modules important for us? So first of all, it's known that M is sigma pure injective if and only if the theory of M is totally transcendental. They are closed on their elementary equivalents, and they are closed on their pure submodules. None of these properties is satisfied by pure injective modules. And moreover, so we know that long limit models are pure injective modules. We know how the first limit model looks like for a fixed lambda. So what can we say about limit model if we assume uniqueness of limit model in some cardinal? So if there exists a lambda greater or equal to T plus, such that KT has uniqueness of limit model with cardinality lambda, then we can show that every limit model is actually a sigma pure injective model. And this will be actually very important. We will use this to prove many equivalences of superstability for the classes we're studying. So we have this theorem. So the following are equivalent. For every lambda greater or equal to T, KT has uniqueness of limit model of cardinality lambda. KT is superstable. There exists a lambda greater or equal to T plus such that KT has uniqueness of limit model of cardinality lambda. And for every lambda greater or equal to T, KT is lambda stable. So it's clear that 1 implies 2, 2 implies 3 is also clear. Now to prove that 3 implies 4 and 4 implies 1, there's 3 things that you need. First, what you do is you prove that limit models are sigma pure injective modules. Then you use the relationship between T hat and K of T. And finally, there's some sort of Cantor-Shutter bursting theorem for pure injective modules. So using these 3 things, basically you can go from 3 to 4 and from 4 to 1. Now, moreover, we can obtain an algebraic characterization of superstability, which in our case is actually more important. So KT is superstable if every model M in KT is pure injective, and there exists a lambda greater or equal to T plus such that KT has a sigma pure injective universal model in KT lambda. Again, the way the proof works is the same. You first look at limit models, you show that they are sigma pure injectives, and then you play with T hat and K. Now, I would like to point out that this 1 and 2, this is the main characterization we care about in all of our examples. So let's look at some examples. So pure semi-simple rings were studied in the late 60s and the beginning of the 70s, and they were given a name in 77. One of the many characterizations is the following. A ring is pure semi-simple if and only if every R module is pure injective. With this characterization and the previous theorem, it's clear that we have the following. So R is left pure semi-simple if and only if the class of modules with pure embeddings is superstable. This is clear because we know that superstability is equivalent to every model being pure injective. Now, Noetherian rings were introduced in the late 1920s. All of us saw them in undergrad as those that have the HCC property for ideal, but actually they have a different characterization, which is important for us. So we have that a ring is Noetherian if and only if every absolutely pure module is injective. Using this characterization, I was able to prove the following. So let R be a left coherent ring. R is left Noetherian if and only if the class of absolutely pure modules with pure embedding is superstable. Again, why do we need this hypothesis that R is left coherent? We need it because under that hypothesis, the class of absolutely pure modules is first order externalizable, and then it's part of the setting we have been talking about for most of the presentation. Now, it's important to point out that actually, to use the results I just presented, this is necessary, but actually you don't need it. So we can actually obtain the following stronger result. R is left Noetherian if and only if the class of absolutely pure modules with pure embeddings is superstable. So since absolutely pure modules in the setting aren't first order externalizable, you actually have to go back and check that everything works out. You have to check that they have amalgamation property, joint embedding property, and maximum models. You have to prove that they are stable. You have to prove that long limit models are pure injective and all that stuff. But all of this works out basically because you have that absolutely pure modules are closed under pure injective embodiments. And the proofs are different in the first order setting and this setting, but they kind of have the same idea. Moreover, Using this characterization, we get the following nice corollary, which relates the stability hierarchy with the axiomatizability hierarchy. So we get the following corollary. If the class of absolutely pure modules is super stable, then absolutely pure modules is first order axiomatized. This is the way you go to prove this is, okay, so if the class of absolutely pure modules with pure embeddings is super stable, then it's Noetherian. Once you know it's Noetherian, this implies coherence, and once you know it's coherent, it's known that then the class of absolutely pure modules is first order axiomatized. Now, in a completely different direction, and using some results from Eckler from the 70s, one can obtain this other characterization of Noetherian rings. So R is left Noetherian if and only if the class of R modules with embeddings is super stable. The proof in this case is very different to what I have been talking about, but it's not that complicated out. Now, with this result, we get the following corollary. So if you look at a billion groups with just embeddings, this is super stable. This is true because we know that the integers are left Noetherian. Now, what happens if we look at a billion group with respect to the pure embeddings? Then it is known that integers aren't pure semi-simple, so we actually get that a billion groups with pure embeddings are not super stable. So here we see that even when we're looking at the same class, and even when the class is first order axiomatizable, the stability properties of the class depend heavily also on the relationship we choose. If we choose embedding for pure embedding, we lose superstability. We maintain a stability, but we lose superstability. So I think this is something interesting that doesn't happen in first order model theory, and it's worth studying. Now let's look at perfect rings. Perfect rings were introduced in the 60s by Bath, and they are very useful in algebraic geometry. One of their many characterizations is the following. So every flat module, so a ring is a perfect ring if and only if every flat module is a projective one. Then what I was able to show is that R is left perfect if and only if the class of flat modules is super stable. The class of flat modules with pure embeddings is super stable. It's very important that it's with respect to pure embeddings because actually flat modules aren't even closed on their regular embeddings. So it's not even AEC if you don't consider them with respect to pure. Now, how does this compare to the other cases? So first of all, flat modules are not first order axiomatizable. I mean, this was also true for absolutely pure modules, but flat modules look even worse because of the following. So flat modules are not closed on the pure injective envelope. So we need to work with contortion modules. Because of this, actually, everything is very different. So at the beginning, I thought, okay, first order will be very different from non-first order, but actually first order and classes that are closed on the pure injective envelopes behave quite similarly. But if you're not closed on the pure injective envelopes, everything changes because instead of looking at pure injective modules, we have to look at contortion modules. What are contortion modules? Contortion modules are just an extension of pure injective modules. I won't define them here since I won't say much about it. And finally, sigma contortion modules aren't as nice as sigma pure injective modules. And actually, the result that you need from algebra for like sigma pure injective modules, I used results from the 70s and 80s. But the results I used for contortion modules were just discovered a couple of years ago. So actually, the proofs are completely different. Now, finally, I would like to present one last corollary. So Artinian rings, as we all saw in undergrad, are those rings that have the DCC property. But actually, it's known that a ring R is left Artinian if and only if it's left perfect and right coherent. Using this thing, we get this characterization of left Artinian ring via superstability. So R is left Artinian if and only if the class of flat modules with pure embeddings and the class of right modules with embeddings are super stable. So this is all I wanted to present. Let me give you some references. So for the first order case, you can look at it in this paper. For the class of flat modules is in this paper, and the class of absolutely pure modules is still under development. Finally, for basic results for classes axiomatizable in first order, but for axiomatizable in first order, you can look at this paper. So that's all for me. Thank you.